Okay, here we go. This is Stats Garage. It's going to be Cohen's D for dependent samples t-test. This is going to do one of the ones from the lecture, the before and after example number 2 question. You don't need to do Cohen's D for the first example in that lecture because that was fail to reject the null hypothesis. Cohen's D, remember, is a measure of the effect size, and it's only relevant when we have rejected the null hypothesis. So, looking back at that problem was a before and after. Students took a test before and after a stats lesson, and we found that the sum of the differences was a negative 49. We found that the sum of squares of the differences was 250.83. And in that problem, the difference score was defined as before minus after. So the negative difference score tells me that students tended to do better. Higher numbers were found after the stats lesson, because the only way I would get a difference that's negative is if the higher number in the subtraction is the second one, right? So there's more higher scores tended to be there. So with this, what do? Well, Cohen's D for dependent samples in this case is D bar divided by the standard deviation of D. If you look back, and you probably should review the slides from chapter 11 about Cohen's D, this was the last slide, the formula for dependent samples. So it's the mean of the differences divided by the standard deviation of the differences. Well, we find the mean of the differences, D bar, by taking the sum of the differences, right, we lowercase, divided by n. So in this case, the sum of the differences was negative 49. Divide that by n, which was 6. Make a note of that over here, n was 6. Negative 49 divided by 6, we found, was negative 8.17. So the average improvement on the exam was 8.17 points. So that mean difference goes here, negative 8.17. And divide that by the standard deviation of D. Well, this is where this test is very similar to a single samples test. We have a set of D scores. It's really no different than what we did with means and standard deviations in the first exam. The standard deviation, any standard deviation, is the sum of squares divided by n minus 1, and then we take the square root. So, the sum of squares of the differences was 250.83. We divide that by 6 minus 1, and we take the square root. So that's 250.83 divided by 5. We take the square root of that. Gives me 50.17. Right, 250 divided by 5 is 50.17, which gives me a standard deviation of 7.08. So the standard deviation 7.08 goes there. Now, I'm figuring these numbers here, but if you did that problem, if you go back and follow along and have done it, those are numbers that would be laying around because we need them to find the t-test. So we're recycling and reusing these numbers. So normally Cohen's D is going to take a lot less work. You do the hypothesis test, you've got the numbers there, you've rejected the null hypothesis, it's time to do Cohen's D. Alright, so what do we have? There's the Cohen's D. D bar divided by the standard deviation of D. Negative 8.17 divided by 7.08 is in this case a negative Cohen's D. I'm going to write that out. Cohen's D equals negative 1.15. Now, in interpreting Cohen's D, I can get rid of the sign, just worry about the magnitude of Cohen's D. That's what matters, 1.15. And according to the criteria that Cohen gives us, that would be a very strong effect. What that means is, right, a difference, an improvement of 8.17 points on this exam is a big difference. 8.17 points doesn't seem like a whole lot, but what that's telling us is given the variability, the typical deviation between students, a group difference of 8.17 points is important. All right, take care.